Hello and welcome to my presentation about Maglev trains. The science, the tech, and the future innovations for my Physics 30 SDS. So let's get into an intro on what Maglev trains actually are. So Maglev trains are monorail style type trains that use the forces of attraction or repulsion of magnets and electromagnets, more specifically, in order to create a levitation off of the track. The name Maglev is actually just a play on what the style of train it is, magnetic levitation. And it was actually created by a Canadian scientist. Like the first Maglev train under that name was made by a Canadian working in America. And so many people call this train, especially the Japanese train, the bullet train, which is just really cool. So how does the maglev work? So most of them use the attraction and repulsion forces of electromagnets to create like a frictionless plane that these trains can slide on. If you think about like an air hockey table, where when you slide the puck across, it's perfectly smooth, there's very little friction to it. This is much the same, except using magnets rather than air. And so they use the magnetic attraction or repulsion to either pull the train along or to push it from behind. So we can see here, this is the levitation. So what we know from magnets is that like poles of magnets will repel each other. So that's what they usually, on the bottom of these trains, they'll have like poles on both the track and the train. And then propulsion of these trains is usually the track is lined with multiple different electromagnets that are constantly flipping from a north to a south to a north to a south pole. And this quick flip-flop, basically the train is now either attracted to or this pole, and then as soon as it flips, it's repelled by it, so it pushes it. So these are some of the types of trains. There's electromagnetic suspension, or there's electrodynamic suspension. So in electromagnetic suspension, it uses attraction from the bottom to lift it up, as well as a little bit of repulsion on the bottom of the train to keep it away, which uses extremely strong magnets, which attracts it forwards. So like I said before, with the poles switching, it uses attraction of these magnets to slowly pull it forward. Well, not slowly, to pull it forward. And it's used in actually the fastest style of maglev train, which is in Japan. And then the electrodynamic suspension is where it uses repulsion just on the bottom and it pushes it up. And this creates a levitation effect. These magnets are super, super duper strong, and they are super cooled and superconducted in order to allow it, even if the main power were to turn off, this train can still use it, can still glide for a little bit before it comes to a rest. And these are usually used in the Chinese style trains, which are more for freight. So some science that's affecting maglev trains, the attraction and repulsion of magnetic fields. This is the main one, obviously. When you're working with a literal maglev train, this allows for the train to levitate. This is what gives it that frictionless plane. And one thing that they have to consider when using magnets is how much load it's going to put on, right? So if I have this, right? This is about 1 gram. This is 1 gram weight. And let's say that we have something that's being repelled. If I put this weight on the top, it's going to slowly add more weight. So the repulsion, as it gets closer, is going to get stronger. However, because of this weight, it's just going to sink. So when you have something like 300 people on a train, that's going to add a lot of extra weight that they have to really account for. So the magnets have to be quite strong. And then our next point would be electromagnets and the current paths. So in order for these trains to have their poles, like right, the poles will change. This is what pushes it forward mostly, and the switching of the poles has to be perfectly aligned with the current path of the electricity that's going through it, or else it'll mess up the timing, and so you'll have a very choppy sort of movement like that. And then our last point, which is actually a very big one too, is friction and wind resistance. So because there's no actual like contact between anything, the friction on the train is actually very low. However, if we want to make a faster train, wind resistance plays a big part. So aerodynamics have to be factored in and multiple other things like that. So the history and development of maglev trains, we'll kind of get into that now. So the history of maglev, so the first references were conceptualized in the early 1900s by Emil Blechach and Robert Goddard. And then Blechach created the first model maglev train using like earth magnets and using earth magnets rather than today's electromagnets. So it was about that big, just a little tiny model of it, but it was the first sort of like idea of, okay, we could definitely use this style of train if it was applied correctly. Now today we don't use earth magnets because they're just not strong enough for our needs. So the first use of the magnet in transportation. So the first maglev train was actually built and used in the British airport in Birmingham to connect the two parts of the airport that were very split. And Berlin also created a maglev train in the early 90s, in order to just solve their overall public transport issue. And I believe it's not in operation anymore. And then our current uses, there's currently six commercial maglev trains that are in use. There is one in Japan, which is the bullet train, two in South Korea, and then three in China. One of those trains in China is a freight train. And the Shanghai Transrapid maglev is currently the fastest ever, with a top speed of over 400 kilometers per hour. So it's very, very fast. So that would take us going to Regina in a typical car from 2 hours to only like 30 minutes, which is crazy. So who invented the maglev? So it's not really one person that created it. It's multiple like people's work over like 60, 70, 80 years. So the first one that was kind of like thinking about it was Boris Petrovich Weinberg. He was the first professor of physics at the University of Tomsk in Russia. He proposed the idea of vacuum transport, which would have been like in a perfect vacuum, you would be able to have very little friction on the train. And he also did a lot of work with magnetic fields and thought about maybe implementing that. However, before he could actually do any work, he was killed in a siege during World War II in Russia. And then Emil Blechach, French-born American inventor who proposed the first model of the maglev in 1914. This was a very big step because he brought it to a very big convention, and it was like, wow, this is something that could happen. And then Hermann Kemper, he was a German inventor who did a lot of research and then creating and patenting for like the basic idea to a like magnetic train. Under his patent in Germany, he has it called it's called a monorail vehicle with no wheels attached. So he still had, but he hadn't gotten really into the like electromagnetic side of it. This was more so like the basic idea that we just built right off of. So there's current projects at maglev. So the Northeast maglev is an American plan to build a high-speed maglev from New York to Baltimore, and it's just planned to be like built mainly for transportation, not freight, and it's hopefully going to reach 300 kilometers an hour. Then the Feng Huang Maglev is a Chinese company that intends to build a low speed line rather than one of these high speed ones, just for transporting like hazardous materials with more precision and less spills. Because of how Maglev works, the ride is very smooth, and so the turns and the bumps are very much like, you won't have bumps like you would on a traditional railroad. So it's very good for like transporting hazardous materials. And then the Tokyo Nagoya Maglev is a plan to build a high-speed track that connects Tokyo to the city of Nagoya. I need to get better at names. And this track is set to be finished in 2027. So some pros and cons to Maglev. So some advantages would definitely be it's less expensive to maintain, and there's less repairs. And this is mainly because of there's no actual contact between the track and the train. So there's less wear, there's less tear on the components of the train. And the lack of contact also prevents the track itself from like degrading and getting a little bit not working quite as right. Environmentally friendly is a very big one. Maglev is totally electric, so there's no burning of fuel or any fossil fuels like that. And it's also very, very quiet. So in cities where noise pollution is a big issue, the Maglev train is almost silent as it goes through. So that's also a very important factor. And then another thing is that it's able to climb higher slopes, which, big whoop, that doesn't sound super exciting. However, with it being able to climb up a hill, the Maglev doesn't have to go through tunnels like a traditional train has to. It can actually go up and go down and still work fine. So some disadvantages. The cost of setup for a train like this is very expensive, just due to the relative like newness of how Maglev transportation works, as well as the energy supply that you have to factor in. That's a big issue. So it's about 4 to 5 times as expensive as a regular train. Another part is the difficulties in acquiring materials. So in order to have a stronger magnetic field, Maglev trains usually use like a lot of rare earth metals, and I think it uses about 15 lanthanides, so those elements. And unfortunately, due to them also being very relatively new, they haven't really found a way for to refine and gather these materials rather than like a standard train, which is just iron tracks, iron materials, stuff like that, which is very easy to find. And then another big one is that it can't integrate into standard train tracks and like how our railroad system is currently set up. This is a big issue because it gets rid of a lot of the land use that, like, a lot of the land that would be used for Maglev, like in a typical spot where you would have a train. And it's hard to say like, okay, we're going to build a Maglev train, so let's get rid of the existing train. So comparison to standard trains. So the cost of maintenance and setup for a standard train is very low cost because the materials are so low, and we've had regular trains for hundreds of years almost. Load size, the typical load size of a freight train is about 12,500 tons. This is with like a bunch of cars behind it, which is extremely good. And the efficiency and speed of these are like a standard high-speed rail for a typical train is about 200 kilometers per hour, which is not anywhere near as fast as Maglev. So in comparison, so maglev trains, cost of maintenance and setup, it has a high setup cost. However, the maintenance cost is very low due to it not having fuel, unlike a regular train. And the frictionless surface keeps it running a lot longer. So load size. So maglev trains are not typically used for freight, and the one in China that's used for it is very low. Like the freight it's carrying is not usually very heavy. So on a typical like maglev train, the passenger size, like the biggest one is 514 passengers. So when you think about it, like if we have every single person at like 150 pounds, it's carrying quite a lot, but it's not carrying anywhere close to a standard train. And then the efficiency and speed of a maglev train, it's extremely fast. Like 400 kilometers an hour is astronomically like fast. Like, however, being fast, sometimes if we were to think about this as a load-bearing train, it doesn't quite come to the standards of a standard train, just because of it just can't carry quite as much, but it's so much faster that it can do 2 trips in the time it takes a train to do 1. So there is that. So my final conclusions that I have, while I think the maglev trains are very efficient, I just don't think that our technology and getting the resources is quite caught up to it. It's just not viable for what we have. The cost of the trains is just too high. The materials are just too hard to find. And until they're made accessible, I don't think that it is like a viable option to have. However, on the flip side of that, as an attraction, maglev trains are awesome. In 2023, I believe, yes, 2023, Japan had over 3 million people ride the train, which, whether that be Japanese people or tourists, you're not always riding the train just for the stats of it, of like, wow, this is a fast train. You're riding this because like, wow, I'm gonna go ride on one of the fastest trains in the world. Like, it's a big attraction for it. And overall, I think the concept of this transportation is a very innovative way to solve like an environmental issue that we have for like typical trains, like diesel burning or coal burning type trains. In actual transport, I think it's awesome. It's very smooth. It's very refined technology. However, viably, I just don't think that it's actually going to be able to work. Thank you for watching my presentation.